So the recording has started. Okay. I would like to welcome our next speaker, Dr. Sangeeta Jha from NIT Rourkela, India. The title of her talk is General Recurrent Fractal Functions and Their Box Dimensions. So I would like to welcome her and over to you, ma'am.
Okay, so thank you, Megha, for inviting this talk. Okay, so today's talk is based on our recent work on the question of general recurrent factor function and their box dimension. So this is a joint work with Honorable Islam Mandal. So, okay, so we know that fractal function. So I think there are several talk already happened on the construction and the discussion on the fractal functions. We all know how the construction has been done. So basically, we know that this fractal function has been constructed using the method of iterative function system. And if you see that iterative function system, by that we mean that we need a metric space and we are using here finite, so we need some number of contraction maps. And in general, mostly we use the contraction map as the Banach one. That is the standard IFS we see. And recently, or not recently, there are long back, there are works on the weaker contraction. And the concept of IFS have been generalized in many different ways. So accordingly, the Barnsley-Hutchinson's theory also have been studied. And so in that direction, one can see that there are work by Celine, Dumitru, Miculescu, and think so like that. So they have many work on these weaker versions of the iterative function system. So mainly what they do is they generalize the IFS using the nonlinearity. And in that direction also, the contraction have been used as the Matkowski contraction, F contraction, and the Milkiller contraction and the Edelstein contraction. So in our talk, we have we have done the construction of the recurrent factor function. So recurrent FIF, that is another generalization of the traditional FIF. So targeting the self affinity in a like smaller scale, the concept of recurrent FIF have been introduced by Barnsley, Elton, and Hardin. So motivated by the work by this Barnsley, Elton, Hardin, and the recent work by Pashupati and Miculescu, so we have like studied this work. Okay. So now coming to the today's talk, we will be discussing on the contraction map we have used is the Edelstein one. So basically, there is a relation between this Mir killer and Edelstein. That's why I just mentioned this. So what is the Mir killer one? So if you have this metric space and if the condition this one is satisfied, then the contraction is the Mir killer one. And if the condition two is satisfied, you can check, then the contraction is on the Edelstein contraction. Okay. And the relation I was talking about that every molecular contraction is an Edelstein, but in general the converse is not true. But whenever you will be dealing with the compact space, then these two coincide. And the reason one can study the concept of Edelstein use the IFS where one use the Edelstein contraction is that the broader set here one can consider that all Banach is an Edel, but the all Edelstein is not in Banach contraction. So in that regard, we have just given an example just to see that it broadened the set. And here we consider the map G as x squared by 10. So if you just check a little bit, one can see that this condition 2 means that this one is satisfied. So this will be an Edelstein contraction. But again, you can check that it is not a Banach contraction. So that's why just one can agree with the case that not all Edel is a Banach one. Okay. And this too is also one need if you want to study new IFS system where we need the construction of fractal function, then the existence and the uniqueness of the fixed point theorem is required. So this was the very traditional result by Eggleston and Mead, where this two is already there. Okay, so now we will come to the our setup. That is the our actual like, work is based on the recurrent one. So here we have used the recurrent IFS, and mainly the contraction map is the Eggleston one. So IFS is consisting of this, and for that reason, we this is just the corresponding setup. According just like when we start with the metric space, and then we define the HX and the Hostop metric. So we all know all this. That's why I didn't define. So similar like that. So accordingly, one can define this HY space. And if you see that whenever your YD space will be compact, then this space will also hold. And this is the definition with the of the recurrent iterative function system. So here we need the probability is required. Okay. This I forgot to mention the reference. This is the reference of Barnsley, Elton, and Harding. Okay, and with the to define this IFS map, just like this small WI we define in the traditional case, in the normal IFS and normal FIF case, here we will be defining that W will be replaced by this W, and this W is the map based on the probability. Okay. And one can see that just like the attractor of the IFS one need for the function construction of the fractal function. First, we need the existence of the attractor corresponding to the IFS. So here our IFS is the recurrent IFS and consisting of the Eidelstein map. And this result, which is very similar, one can easily prove this one. So if you are dealing with the contraction map as Eggleston contraction, and if you consider this W, this map, this one, then this also has a unique fixed point. So this A bar here, we have denoted this notation, is an attractor, and it satisfies this equality. So with an example, we have just elaborated the above construction. So here you consider the maps W1, W2, W3. So here one can note that the difference we have seen is we didn't take all the Banach. The W2 and W3 are not the Banach map. One can check this one. And if we define this, if we use this notation, then one can check that this A bar will come as the attractor of this RIFS, of this recurrent IFS. This A bar is the attractor. Okay, so now we will come to the construction of the recurrent fractal interpolation function. So with the above setup of the this IFS, this attractor, now we come to the function. So as like we know that for the constant factor function, we usually need two set of maps. One is the contraction in this x direction, and another one is the contraction in the y direction. So these are the maps ln and fn. So accordingly, this LL and FN and the joining up condition, all this has been tackled here. And with this WN, this is our new RIFS. And the just like this Barnsley's thing, that existence of the graph will be there. So this is the result. And you can see this paper, the full proof and everything you can find here. So if this is the setup, so based on the setup of this, so if this is the IFS, recurrent IFS, then there exists a unique continuous function F star, which interpolates the data set, and this graph is the invariant set. So that's why our F star we denote as the recurrent fractal interpolation function. So here also I have given one example for the illustration. So just start with some data points. Some random data points have been taken, and this contraction map, we just use this 4 contraction map we needed here, and we need that matrix using the probability. We just constructed the connection matrix, and corresponding figure we have generated. I'll just go back. Uh, So these are the four different figures. So first one is the our classical Barnsley FIF, where we use the Banach contraction for the same data set. And this one is the corresponding using Banach, the recurrent fractal function, which is also there. This first one is also available in the literature. This one is also there. And the last third one is the course, just use the Edelstein contraction instead of the Banach one, use the contraction as the Edelstein one, then construct the fractal function for the same data set. So all the four figures are for the same data set. And we are just in the different cases. First cases, we are using the contraction as the Banach one. The third cases, we are using construction as the Edel one. And this first A and C are the A5F and B and D are the RA5F. Just to see that there are the differences, the four different structure has been given. So this one, the last one is the recurrent fractal function using the Edelstein contraction. Okay. So one can just see the, depending on the contraction, the graph has some changes. Okay, so our main work or main theme was to try to find some upper and lower bound of the box dimension of the graph of this particular iterative function system. So in that direction, we have so these are the few setup is required to give an upper bound and lower bound. So here, so you know that was box dimension. That definition was we need to do some covering. So here we are using this just like your n delta. So this is the function our here. So usually we write n delta here when we number of balls we count, number of boxes. So in for our case, we have used that part as m epsilon. So this is the box length of side length epsilon, and this is the definition of this epsilon partition. Okay, and okay, so the boxes we have used is actual boxes is this script tree, and just for simpler calculation, we have used our data points as n by m, and the interval we have taken as 0, 1, so that like competitions will be an easier one. And these WN maps are the NX and BN and CNX SNY. So this SN. So this is the main one. So this SN are the non-linear one. So usual case what we do is we just write SNY. That is the linear, mostly linear part we use. And here the our construction was based on the Edelstein one. So which affects the non-linearity. So accordingly, one can calculate matching based on this matching condition, this joining up condition. One can calculate this N, BN, CN, all these term can be calculated. Now with fixing all this, if we consider these boxes as this one, and we also need that one help we need here. Here again, I think I missed the references. So we need this is the, you can see the book by, I think, Positive Matrices. So if you have a irreducible non-negative square matrix, then the spectral radius is an eigenvalue of J, which corresponds to a strictly positive eigenvector Y dash. So we'll be using this result to give the main upper bound of the dimensions. The main upper bound is, so this result is the actual one. So what it says that if you suppose this C is the irreducible connection matrix for the RA5F and DLD is the diagonal matrix. So just write DLD equal to diag of this one. So if the spectral radius is bigger than 1, then this D is the unique number such that the spectral radius of this matrix will be 1, and then our graph of this dimension will be less than. So this will be the upper bound then. So to prove this result, which is the main content of our work, we need this theorem 12, which you can find in the book of the positive definite matrices, and and to give the lower bound. So this one is corresponding to the upper one, where I didn't mention the full proof. You, you can see the paper which is available now. So full proof is there. So basically, with the one need to consider the boxes like this, and then that cover and that the spectral that matrix. Then we need to calculate the spectral radius. So totally, it is totally based on the spectral radius part. Okay, then we will get the upper bound, and to get the lower one, we need to this lemma will be useful. Okay, so if we use this lemma, then again here also this VSN and this part is a little bit long, and I think I missed that upper constant also is missed here. Okay, so this LSN, this capital LSN, this notation also is missed here. Mm, did I include VSN? No. Okay, okay. So this upper bound result is the we need the help of the previous lemma. Hmm. So based on this lemma, we have this lower bound. So this number is the unique number. So when where the spectral will come, then the box dimension, the lower box dimension of the graph will be at least this delta. Okay. Okay. So maybe with an example, one can see. Okay. So before I go to the example, this is just a remark that what will happen when will reduce to the traditional IFS, then from this result you can get back the box dimension of the classical FI. Okay, so just take this all the elements to be one. So if the connection matrix is this one, then it will be actually the standard IFS. And since in our cases we are able to give the all the calculation was in this interval 0 1. So when you take this interval as 0 1 and consider all this uniform partition, so accordingly, we just need to calculate the matrix, which will be this. So this capital LS and this small LS, these were actually the upper ellipse is constant and the lower ellipse is constant. So which I didn't define. So with the help of those two constant, one need to construct the matrix, and then after constructing the matrix, just calculate the spectral radius. Okay. And if we just one second, if we use this result, then we can check that whenever the spectral radius is bigger than 1, then this will come. Okay, so whenever this sum of ellipses this capital is the upper ellipse is constant. Okay, and whenever I use the small LSN, this is the lower ellipse is constant. So it will come, it will reduce that this t will be the. So using this theorem 13 means using our result, one can deduce the box dimensional result of the classical one. So this relation is bigger than 1, this spectral radius will also be bigger than 1. So our theorem will reduce that this upper dimension will be less than equals to this script t, which is the unique number. And you can check that whenever this L of Sn, that is mean the lower ellipse is constant if we will use. And if we will use this theorem, this one, it will reduce. So all this remark is totally about, it is just concerning that if from this result we are getting, whenever we use the connection matrix to be this one, we will get back the theory related to the usual IFS. Okay. Okay. Now here we mentioned, we have just given one example, and we we used one connection matrix. So you can see this picture denotes the corresponding this one. And when we have the data point is this one, and the sub intervals we are taking this part. Okay. And then we calculated that. So all the matrices. So to calculate this, the spectral areas, first of all, you need to write down the matrix, the diag matrix, using the lower ellipsis constant and the upper ellipsis constant. If you calculate all this, then you can find that this will be the spectral radius, which is coming as bigger than 1. And if you find the characteristic equation, so all these steps are involved for the calculation is not a trivial one. So one need to calculate the matrix part, you need to calculate, they need to calculate their spectral radiuses, one need to calculate this for the spectral radius, one need to calculate this characteristic equation of this matrix. So this DLDC, this is nothing but that diag matrix. Okay, concerning the that contraction SN map is there. Those SNs are the ideal strand contraction. So here I think I didn't mention all. In the paper it is there. What are the maps we have used? So depending on the maps, one can construct the matrix, and after that one can see check the spectral radius, then see what will be the what is the way that is coming as bigger than 1, then the value for which it is bigger than 1. So that number will be our dimension. So here it was coming as, for this particular examples where the data points are this one is coming as 1.67. The full details, I didn't mention all the parts. The full details are there in the paper. You can check it. The main idea is one, the how to handle the non-linearity of the map SNY. So since we have used this in the IFS construction, we have used the contraction map as the ideal one, and accordingly our IFS has become nonlinear. So to do all the calculation, the nonlinearity need to be handled. So here we have handled it via using the lower ellipsis constant and the upper ellipsis constant. Okay. Okay. So thank you. If you have any question, you can tell. And the references, I think this there. Did I mention? The main references was the recurrent IFS by Barnsley, Elton, Hardin, and the recent work by Pashupati and Mikulescu about the fractal function corresponding to the Edelstein contraction. Okay. So if you have any question, you can just ask.
Okay, thank you, ma'am. Thank you so much. So I think there is a question.
Yes.
So the question is in the chat box.
Oh,
Do these
I'll check.
results? Yes. Okay.
I'll just check. Okay. Okay. Do these results generalize to phi contractions? If not, how do they compare with the results obtained phi contraction assumptions? See, like just in the first, I told that fractal functions have been generalized in many different ways, just like weakening the contraction condition, the space, and like generalizing the IFS. So, in that respective, particularly which one you want to generalize? Like what particular generalization you are talking about? So the main target, you can, is phi contraction, there are many work. Fractal function have been constructed using phi contraction. This result is already there. Okay. So if you are saying you want to compare this, so do you want to compare this construction with the phi contraction, or which one you are talking about here? You can just, I think the mic is there. You can just tell. No need to write down now.
Ma'am,
Uh,
Huh,
like
huh.
the Matkowski and the Rakoch contraction, basically,
Yes.
and like, yes,
Hmm.
ma'am. So I
Okay,
was
it is
thinking to
there.
do that.
You are thinking to do, but the fractal function construction using your Matkowski and this file is already there. So every time what one they are doing is one need to check whether the Barnsley-Hutchinson's theory is applied or not. That is for the first construction part. After you do the construction, then you look for about its dimension. So whether you are able to give any dimension work. Now for different setup, this ultimately you need to just cover it. If you are doing this box dimension, you need to find its cover and then you need to calculate all those calculations. So based on your IFS, like your bound will come. So better bound or like tighter bound, stricter bound, different bound will come. So comparison, if you are saying like, if you just say that compare from FIF to RFIF, then RFIF is the more generalized version. So here targeting your, um, here you are targeting the self similarity or the self affinity, not in the border one. So in a different intervals, different type of similarity will be there. So whenever your data will be coming from those set, so then RF you use your RFIF. Whenever data is self similar in every scale, it is self similar. Then you don't need the RFIF. In that case, our classical FIF will be helpful. So depends on what type of data we need actually. If you someone say in the application perspective, then we need to select what we want. If we want the simpler versions, then we'll not go for nonlinear IFS and targeting that part. Whenever the nonlinearity is required, so these theories are available. Now, depending on our demand, we will be using that part. Okay.
Okay, ma'am.
And so if I'm not specific, you can just tell, like, do you want to work on phi contraction you are saying?
Yes, ma'am.
What I'm saying, it is there. It's there. Like fractal function have been, see, what people are doing is there are many weaker contractions available. So when we want to generalize it, they are just searching like whether this Barnsley's Hutchinson's theory is applicable or not. So for the construction of the attractor, first target is you construct the attractor, and then using the attractor one, you generalize the Barnsley's theory for the construction of the function, and then you come to the dimension part. These are the three steps we usually use. So for the case of your phi contraction and your F contraction, the construction part is already there, available. Okay.
Yes,
Hmm.
dimension result is not given yet
I
for
think
the most.
dimension was for the Matkowski dimension might not.
Mm.
I think I have seen the Songil Lee has been given the construction for
Yes,
phi
he has given the
and
construction only, not the dimension part.
construction. Hmm. And for the case of this Edelstein one, the usual Edelstein one, this recently this Pasupati's work, what I was talking about. So
Oh,
they have given the construction and the dimension of the Edel one. Okay. And what
mm.
we have given is we have given the dimension and the construction part for the recurrent one.
Yes.
And since this is the mostly weaker, the ideal one is the almost the weaker version. So this is more adaptable than your phi and the Matkowski. So that's why this has been studied.
Okay,
Mm.
ma'am.
Okay.
So
Thank you, ma'am.
if there is any more question from the audience, if not, so let us thanks the speaker. Thank you so much. Okay, so our next talk will be in 2 minutes.
Oh, okay. I just stopped here. Okay.